Welcome back, calculus friends. This is AP Calculus section 5.1 notes. Today we are going to be transitioning to the other side of calculus. We've spent all of our time this year so far talking about limits and derivatives and applications of derivatives. So now we're going to switch to the other half of calculus, and soon we'll see how these two halves are related to each other. But the other half of calculus has to do with areas and distances. So suppose we were given a function f of x and we were asked to find the area under the curve from x equals a to x equals b. So if we look at the picture on the right hand side of the screen, we would be talking about this area right here from x equals a to x equals b. The easiest way that we can do this is by approximating the area by dividing that into smaller chunks and approximating those areas and then adding them together. And in this instance, when we're trying to estimate area under a curve, one of the easiest shapes that we can use is rectangles. So these three pictures below here kind of illustrate the idea that we're going for, right? The formula for area of a rectangle is just its base times its height, so it's an easy area to calculate, and then we can just add up our areas to get an estimate of the area under the curve. Now, the difference between these three pictures is that obviously we are using more rectangles in picture number 2 and even more rectangles in picture number 3. And I'm sure that you can assume that our areas are going to become more and more accurate as we use more and more rectangles, because the overhang here on the top, the extra area, becomes less and less as we use more and more rectangles. So for the following examples, we are given the graph f of x equals x squared plus 1. And we are going to estimate the area under the curve in multiple different ways. So in part A, they are asking us to estimate the area under the curve by using 3 rectangles with right endpoints. Okay? So the 3 rectangles, then, it makes sense since our x-axis goes from 0 to 3. That was the given domain that we're trying to find the area under the curve for. So if we're going to be using right endpoints, then our first endpoint is going to be right here. Our second endpoint is going to be right here, and our third endpoint is going to be right here. That's what we mean by right endpoints. So our 3 rectangles then will look like this. And those are the 3 rectangles that we are going to use to estimate the area under the curve. So we just have to figure out what the areas of those 3 rectangles are by taking base times height. Well, looks like the height of our smallest rectangle is 2, and the base of all 3 of our rectangles is a unit of 1, right? So 1 times 2 would be 2 for the first rectangle, plus our second rectangle, base of 1. It looks like it has a height of 5. So 1 times 5 would be 5, plus, and then our third rectangle has a base of 1 and a height of 10. So 1 times 10 is 10. And we add those together, and we get an approximate area of 17 units squared. Now, looking at the picture, we know that this is an overestimate, right? Because the tops of our rectangles go quite above the curve when we're using right endpoints. Okay, now in letter B, it's asking us to do the same thing, except this time it wants us to estimate using 6 rectangles and right endpoints. So now we're going to be dividing our space into 6 rectangles. So our bases of our rectangles now are going to be 0.5 instead of 1. And this is what our picture is going to look like for right endpoints. And again, when we talk about right endpoints, these dots that I am putting here are the right endpoints. So this time we have 6 rectangles, and the base of each of our rectangles is 1/2. So just to simplify the math a little bit, I'm going to put the 1/2 outside, and then I'm just going to add all of the heights together for the 6 rectangles. The first rectangle has a height of 1. The second rectangle has a height of 2. The third rectangle has a height of 3. The fourth rectangle has a height of 5. The fifth rectangle has a height of 7. And the sixth rectangle has a height of 10. So you add those together, you get 28, and then you multiply by 1/2, and you get 14. So obviously, this is going to be a better estimate because, first of all, it's less than 17 units squared, which we knew was an overestimate. Since this is also still an overestimate, but yet it's less, we know that this is better. Okay, but I do want to clarify that these are overestimates of our area because we have that overhang above the curve. So now we're going to switch gears a little bit and we're going to use left endpoints. So if we use left endpoints, this picture is going to look a little bit different because then our left endpoints are going to be here and here and here. And so our rectangles are going to look like that, and like that. And these are the areas that we are going to be adding together. So you can already see that using left endpoints, because our function is increasing, is going to cause us to have underestimates for our area values. And again, our areas are found the same way because these are 3 rectangles, so we multiply the base times the height. The first rectangle, base of 1, height of 1. The second rectangle, base of 1, height of 2. And the third rectangle, base of 1, height of 5, which you add 1 plus 2 plus 5, and you get an area of approximately 8 units squared, okay, which we know is an underestimate. And now we're going to do it again, but this time we are going to do it with 6 rectangles. Oops. So again, I'm just dividing each of those big rectangles into 2 rectangles. So here are our 6 rectangles. And again, to calculate the area here, I'm just going to put the 1/2 for the bases of the rectangles on the outside, and then I am going to put the heights in here. So it looks like both the first rectangle and the second rectangle appear to have a height of 1. The third rectangle looks like a height of 2. The fourth rectangle looks like a height of 3. The fifth rectangle, height of 5, and the sixth rectangle, height of 7. And so when you add that together, you get 19, and half of 19 is 9.5. So again, we know that 6 rectangles has to give us a better estimate than 3 rectangles, yet we still have an underestimate of our area here. However, we would say that 9.5 is a better estimate, just like when we did our right endpoints, we would say that 14 was our better estimate. So it's safe to say right now that our area under our curve has to be somewhere between 14 and 9.5, right? Well, the question is, can we do any better than this? And of course we can do better than this, because the best way to estimate, so I'm kind of answering letter F already, is that we want to use midpoints, okay, for our rectangles. Not left endpoints, not right endpoints. We want to use midpoints. Okay, so what do midpoints look like? Well, if I were to divide my x-axis up into 6 pieces, so I'm going to do midpoint rectangles with 6 rectangles. Then those are my 6 bases there along the x-axis. And if I am going to use a midpoint, then the height of the rectangle I'm going to put exactly in the middle of the interval. So my midpoints are going to be in these locations right here, exactly in the middle of the interval that I've created on the x-axis. So now my rectangles look like this. And so you can see that with the midpoint rectangles, I have a little bit of an overhang above the curve, but then I also have a little bit of an underhang. Overhang on the left side, underhang on the right side for each rectangle, which you think probably sort of cancel each other out. So I would expect that this is going to be our best estimate. So let's calculate what we get when we do the area of these rectangles. Again, our bases are all 1/2 because our x-axis went from 0 to 3, so each rectangle has a base of 0.5. And if we calculate the heights of each of our rectangles, the first rectangle has a height of 1, the second rectangle a height of 2, the third rectangle a height of 3, the fourth rectangle a height of 4, the fifth rectangle a height of 6, and the sixth rectangle a height of 9. And when you add those together, you get 25, and half of 25 gives us an area estimate of 12.5 units squared. Okay? So to answer letter F, which of the above seems to be the best estimate? The answer is midpoint rectangles seem to give the best estimate. And this is because the parts of the rectangle above the curve and below the curve seem to cancel out some of the error in the area. Right? So just to clarify what I'm talking about when I say that, here's the area above the curve and here's the area that's not counted, right? Those kind of seem to cancel each other out. Same thing right here and right here, right here and right here. So it's not perfect, but it's certainly better than what we had when we did either left endpoints or right endpoints. This brings us to a definition. The area A of the region S that lies under the graph of the continuous function f is the limit of the sum of the areas of approximating rectangles. So we're not done with limits yet. The idea here is if we could take as many rectangles as possible and smush them together under that curve, then the area would be the limiting sum of the areas of all of those rectangles. If we could take the number of rectangles to infinity, basically we'd be able to pinpoint the exact area under the curve. And so when we talk about adding up a bunch of things or finding a sum of a huge number of numbers, we often use sigma notation in mathematics. Sigma notation is that symbol right there, which just means that we are finding a sum. So we can use sigma notation to express the area under any curve as a limit. So our next example here, we have this graph of y equals x cubed just from x equals 0 to 2. And using right endpoints, they want us to find an expression for our area as a limit. Okay, now this is kind of complicated. I don't want you to get too stressed out over it. You need to see this at least once, but it's not really going to come up a whole lot. But I do want you to be familiar with the way that this is written and the idea of area being a sum of rectangles under a curve, okay? So if we are finding right endpoints and we want to find an expression for area as a limit, the first thing that we need to figure out is the width of each of our subintervals, which is always, the change in the x distance. You're going to want to write small, just so you know, because there's a lot that has to go in the space between letter A and letter B. Okay, so the width of a subinterval is delta x, is what we call it, is equal to b minus a divided by n. Or in this case, 2 minus 0, because that's our b and that's our a, divided by n, okay, where n is going to be the number of intervals, right? So this is going to be equal to 2 over n. So that's our delta x. And then we have to figure out, well, what are our endpoints going to be then for our rectangles? And since we're using right endpoints, our x sub I values, that's what we call them, those are the endpoint values, our x sub I values. Well, the first one, again, using a right endpoint, would be just whatever 2 divided by n is, right? Because that would be the length of the first interval. So, whoops, I should say x sub 1 is going to be equal to 2 divided by n. Our endpoint of our second interval, so we'll call that x sub 2, is going to be equal to 2 times that distance 2 divided by n. Our x sub 3 is going to be equal to 3 times our distance 2 divided by n. So you can kind of see the pattern that we have going here. So any term x sub n is going to be equal to n times 2 divided by n. And so now that we know what our widths of our subintervals are, or basically the bases of our rectangles, right, is 2 over n, and we know the endpoints of our rectangles, we can figure out an expression for the sum of the areas of the rectangles. So that's next. We're going to call that r sub n. And again, the area of each rectangle is going to be the base of the rectangle times the height of the rectangle, right? So the first rectangle would be the height of the first rectangle. So f of x sub 1 times our base of our rectangle, which is delta x. And our second rectangle would be the height of the second rectangle times delta x. And the third rectangle would be the height of the third rectangle times our delta x. And again, we could keep going and going. And the area of our final rectangle would be the height of the nth rectangle times delta x. But we know what delta x is. Delta x is 2 over n. And we have an expression for our endpoints, or our x sub I values, so that's our heights, or our f of x1, our f of x2, so on and so forth. Okay, so we can go ahead and we can plug these values in, and we can come up with an expression using those terms that we've created. Okay, now we know that our function is y equals x cubed, right? So the height of our function, or our f of x1, is going to be our x1 value, which was 2 over n, plugged into our function, which is something cubed, so it's going to be 2 over n cubed. Again, that cubed comes from the fact that our function is x cubed. And then times, so that's the height of the first rectangle, times the base of the first rectangle, which is our delta x, or our 2 over n. Okay, our second rectangle is going to be the height, which is 2 times 2 over n, cubed, times our base, which is 2 over n. Our third rectangle is going to be our height, which is 3 times 2 over n cubed times our base, which is 2 over n. And then finally, our nth rectangle height is going to be n times 2 over n cubed times 2 over n. And so when we look at this, obviously we're going to be taking the limit as n goes to infinity of all of those rectangles. Okay, so we can do some simplifying here. I'm going to need to create more space for myself. So our area is going to be equal to the limit as n approaches infinity, right? Because the idea here is that we can create as many rectangles as we want under this curve, and if we take n to infinity, it's going to be basically an exact approximation of our area. So the limit as n goes to infinity of our r of n that we just came up with in the last step is going to be equal to the limit as n approaches infinity. Now, when I look at each of my terms, notice that every single term is the areas of each rectangle are multiplied by 2 over n because the base of each of the rectangles is the same. So I'm going to factor that 2 over n out. And then what's going to be left in each term is just going to be the height of the rectangle. So the first rectangle is 2 over n cubed. And the second rectangle is 2 times 2 over n cubed. And the third rectangle is 3 times 2 over n cubed, so on and so forth. And the nth rectangle is n times 2 over n cubed. Okay, and I can simplify this further by using summation notation. So I can say that this is going to be equal to the limit as n approaches infinity of, I still have that 2 over n in the front, but now all those things that are being added together, that's my sum, right? And so basically I am looking at, there's my summation notation, so I'm looking at the sum from I equals 1 to n, and then I have to come up with an abbreviation that's generic for each of those heights of those rectangles. Well, the number in front that's being multiplied times the 2 over n, that's going to be whichever term it is. So we're going to say that's going to be our, our I times, and then we have the 2 over n, and it's always cubed, right? And then I can simplify this further. So I can say this is the limit as n approaches infinity. I've got the 2 over n outside, got my sum from I equals 1 to n. But now what if I take that cubed and I sprinkle that inside the parentheses here, and I cube everything inside? Then that's going to become 8i cubed over n cubed. Okay, but now my summation notation is really just about the I values. So anything that contains the n can be pulled out in front of the summation. So my almost last step here is going to be, this is the limit as n approaches infinity of, I've got the 2 over n times, I'm also going to bring the 8 over n cubed out in the front, because again, the summation doesn't depend on n, it depends on the values of I that we are plugging in. And I still have I equals 1 to n of I cubed. So finally, we can simplify what's in front of that summation symbol. So we have the limit as n approaches infinity of 16 over n to the 4th power times the sum from I equals 1 to n of I cubed. Okay, so this is our answer. we have successfully written the area under the curve as a limit using summation notation. This was not an easy thing to do, and I am not going to expect you to reproduce anything like this on a quiz or a test. But it is important that you've seen it and that you understand the idea of writing the area under a curve as a limit. Part B, they want us to estimate the area by taking sample points to be midpoints and use 4 subintervals, and then do it again and use 10 subintervals, okay? But again, we're using the same function, y equals x cubed, on the interval along the x-axis from 0 to 2. So the first thing that I'm going to do is I'm going to just sketch a little picture of our curve. It doesn't have to be exact. We just want to be able to draw some rectangles on it. So here's my curve. Looks something like this. Here's x equals 0. Here's x equals 2. Okay? So if we're going to use midpoints and we're going to use 4 subintervals first. So our n is equal to 4. The first thing we need to do is we need to find our delta x. So our delta x is going to be b minus a, so in this case, again, 2 minus 0 divided by the number of subintervals, which is 4. So that tells us that our delta x is going to be 2 over 4, or 1/2, or if you prefer, 0.5. So those are going to be the bases of our rectangles. Okay, so let's draw our rectangles here on our picture. So if we're going to be doing 4 rectangles and we're going to be doing midpoints, then the first midpoint will be there, second one will be there, third one will be there, and fourth one will be there. So visually, this is our picture of our 4 rectangles. Okay, so if I label those tick marks that I put on the x-axis, this would be 1, so this is 0.5, so this is 1.5. And our midpoints are going to be those values in between, right? So right here, right here, right here, and right here. So our area is going to be equal to the base of all of our rectangles, which is 0.5, times the 4 heights that are at those midpoint locations, which are going to be f of 0.25, f of 0.75, f of 1.25, and f of 1.75. So how do I get those? Well, I plug those numbers into y equals x cubed. So I grab my calculator. What is 0.25 cubed? What is 0.75 cubed? Because our function is y equals x cubed. So those areas, those values of the function, those heights, are 0.015625. I'm carrying a lot of decimal places because I want to be accurate. My second height, f of 0.75, is 0.421875. My third height, f of 1.25, is 1.953125. And my fourth height, f of 1.75, is 5.359375. So you add those together, you multiply by 0.5, and make sure that you are reporting your answer to 3 places past the decimal, because that's the expectation of AP. And so we get area is 3.875 units squared. Okay, so that is the area approximation that we got using 4 subintervals. So now they want us to do the same thing, but this time they want us to use 10 subintervals instead of 4 subintervals. So we are going to start the exact same way. We're going to create a little picture here for ourselves of what this looks like. from 0 to 2. But this time we're going to divide it into 10 subintervals. Okay, so when we do that, each of these are 2/10, right? So 0.2, 0.4, 0.6, 0.8, 1, 1.2, 1.4, 1.6, 1.8, and 2.0. And when we draw our rectangles, our midpoints are going to be at the odd decimals, right? So our heights are going to be at 0.1, 0.3, 0.5, 0.7, 0.9, 1.1, 1.3, 1.5, 1.7, and 1.9. And you can already see that just based on the picture that this is going to be a more accurate representation of our area. The more rectangles we have, the better our areas become. So this time with 10 subintervals, our delta x is going to be, again, b minus a, so 2 minus 0 divided by n, and in this case, n is 10. So we get 1/5 or 0.2. And our area then is going to be equal to 0.2, that's the base of every rectangle, times the heights of each of those rectangles, which would be f of 0.1 plus f of 0.3 plus f of 0.5, 0.7, 0.9, 1.1, 1.3, 1.5, 1.7, and 1.9. Right? And so now we grab our calculator and we have to find all of those values again by plugging them into x cubed. So for the first one, what is 0.1 cubed? What is 0.3 cubed? What is 0.5 cubed? So I use my calculator to calculate those. So I get area is equal to 0.2 times, I'm not going to use as many decimal places this time. I'm just going to go 3 places past the decimal. So 0.001 plus 0.027 plus 0.125 plus 0.343 plus 0.729 plus 1.331 plus 2.197 plus 3.375 plus 4.193 plus 6.859. Be very patient with your calculator. It is your friend. Okay, and then we are going to add all those together, multiply by 0.2, and we end up with our area is 3.980. Okay, so obviously more accurate. Now, an interesting thing to note is that the actual area here is 4. So the more subintervals we use, the closer we get to the actual area. Okay, so you might want to make a little note. The actual area under the curve y equals x cubed from 0 to 2 is 4 units squared. So the more rectangles we use, the better our estimate for area. Okay, so just an important note to make. The more rectangles, the better, because that's the more accurate area under the curve.